Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2023 Northern Hemisphere Chemistry Exam Multiple Choice Part 2 of this section. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 18. Consider the following molecule. What is the International Union of Pure Applied Chemistry IUPAC name of the molecule shown above? Easy. So, we can see that there's actually two functional groups. We can see that we have a hydroxyl group, which is an alcohol, and we also have this basically an amine group. Now, we need to see which one has the highest priority. Now, remember, one of the most easiest way to know which one's the highest, if it has an oxygen. Those that have the most oxygen tends to be the most priority. Like, for example, this one has oxygen. Normally, the alcohol has oxygen, so it's going to be an alcohol. The name is going to be an alcohol. So, at the end of the molecule, it's going to be named an alcohol. So, let's have a look at the names. Look, amine, these are wrong. It's going to be named as an alcohol. So it's one of these. Beautiful. Now, when I look at it as a skill leader, this one looks just not that nice. I'm like, it's kind of a little bit too much at once. So I'm just going to break it down into its structural formula. So we have one here, carbon, one carbon here, one carbon here. It's 3. So 1, 2, 3. We have, the amine group here. And we have hydroxyl, so oxygen, and we also have an methyl group here. All right, this is what it looks like. Beautiful. Now, what is the longest chain? What is the longest chain? Well, it's this one here. It's that 3 C's, basically. So it's a propane. It's like a propyl group, so propane. And beautiful, so it has to be a propane. Easy. Now, where do we cut the numbers? Where do we cut those numbers, basically? Like, do we count it from, which carbons do we count from? Like, if I look at it here, do we say 1, 2, 3? Well, if you do that, okay, we hit the hydroxyl group at 2, which is good. But what about if I do it the opposite way? 1, 2, 3. We still hit the hydroxyl group at 2, but it's better this way. Because we hit at 1, we hit the most quickest way we can hit the amino group, amine. So, now we've hit the amine group. What we're going to basically do now is, that's it. So, 1, 2, and 3. So, it's going to be basically propane 2, so it causes the hydroxyls 2-ol. Now, it has an amine group at the carbon 1, which is going to be 1 amino. And of course, don't forget this also methyl group, and it occurs at the 2. So you would say, like, 2 methyl. 2 blah blah methyl. So it should be something like that. 1 amino, 2. Yep, this one is perfect. You look like C is the perfect one there. Done. Question 19. Consider the following molecules J and L. Alright, so J and L. The boiling point of J is what? Higher, lower? Okay, let's first look. Let's have a look at J first. Okay, J looks good, but we have like a nice amide group here. See that we see like this nice amide group here. So, okay. Whereas if we look here, so we can see that it has more carbons. And it has a hydroxyl group here. Now, we know, okay, let's think about the best way to know which one has a higher bond, the more it forms hydrogen bonds, the more it has a higher bond. But remember, the hydrogen bonds are the strongest intermolecular forces you can have. And yeah, so looking at this here, we can see that, yeah, good. We have like a oxygen here that can actually form those, hydrogen bonds. And we also have nitrogen. Also, nitrogen forms hydrogen bonds. So this is good. So it has like 2 sites where hydrogen bonds can occur. In comparison to this, where it only has 1, so, all right, that's a kind of a hint of telling us which one should have. So it looks like J probably has a higher boiling point. Now, when we're looking at dispersion forces, both have dispersion forces, but are they the same? It depends in the molecular formula or the molar mass. Now, I'm looking at this. Okay, this has 3 carbons, okay, whereas this one has 5 carbons. Now, you would think, like the chain, this would have higher dispersion forces. Yeah, but remember, dispersion forces are the most weakest. It's not the strongest. Having 1 hydrogen bond is stronger than most of the dispersion forces that you'll have in a molecule. So absolutely, J has to be more stronger molecule than L, because there are more sites of hydrogen bondings. The boiling point of J is what? It's higher. So take C and D out. Because what? J has weaker dispersion forces? Nope. Yeah, it doesn't probably have even dispersion. They could probably have the same dispersion forces. Depends on the molar mass. But yeah, it's not about the dispersion forces, so that's not right. B, higher than L because J has more hydrogen bonding sites. Beautiful. B is correct. Remember, it has more so it has more oxygen than nitrogens, hence these are the sites for hydrogen bondings. And absolutely, yeah, nice, easy question. Question 20. Let's have a try this. Consider the following triglyceride. We have this, beautiful. When this triglyceride is hydrolyzed, one of the products is what? Okay, so we know that when we hydrolyze, so break these bonds right here, cut these bonds, we form a 1-glycerol, molecule, glycerol, and we also form 3 fatty acids, which are these parts here. These are your 3 fatty acids. Now we need to check. Let's look at the first part. One of the products is this. Now, we know one is glycerol, which has oxygens. This doesn't even have oxygens. It could be one of our fatty acids. Let's check. So it has 3 carbons here. And it's basically like a straight chain. No, absolutely not. Look at these. This has how many carbons? Wow, a lot. We have 17 here, plus one there. We have so much carbons here. Yeah, this one only has 3. This is rubbish. Not even anywhere. Doesn't exist anywhere here. Is it linoleic acid? Let's write linoleic acid. Let's find what it is. Linoleic acid. In our data book, there it is. Linoleic acid. So it's the one, this one here. So let's write its actual formula. I think that's going to really help us. So it's a C17H31 COOH. Done. That kind of should give us a hint of what it could be. Now, remember, so of course, you have this parts where basically when you break them, you'll get this group back, where this is that carbon and this is that oxygen. Easy? Now, it's just this part we need to find which one has. So it has to have 17 carbons. Let's check which one has 17 carbons. Does this one have 17 carbons? So looking at this, we have 7 here. 1, 2, we have 2 here. 7 here. 1, so that is 7, 14 plus 3. We have actually 17 carbons. Good. This fits. It looks like it's doing well. So we do have 17 here. Do we have 31 hydrogens? That's the key now. Now, let's check. So we have 14, so we have 14 here in this part. We have 2 in here. We have, again, 14, and we have 3. So basically, we have 30 plus 3, which gives me 33. Nope. We're supposed to only have 31, so that is wrong. In that molecule. It's not in that molecule. So that's basically wrong. Next one. We have how many carbons here? We have 17 here. Plus 1, so we have 19. Wrong, we're supposed to only have 17, not that one. All right. This one over here, we have 5, 1, 1, 1, 1, 1, 4, 1. So basically we have, these are 10 if we consider them. 1, 2, 3, 4, 5. We have 15 basically, C15. We have, okay, carbon, yeah, C15, which is wrong. It doesn't even have, we're supposed to have 17. So not even linoleic acid is even in it. So, all right, that's we're breaking out. What is it? Omega-6 3? Is it omega-6 fatty acids? Remember, to find out if it's omega-6, you're going to look at the right-hand side and count till you hit the double bond. For example, we have 1 here. We have 4 here, so if that's 5, 6, 7. This here, when we hit that double bond, we're hitting the 7th carbon, meaning it's a omega-7, not omega-6. This one doesn't even have carbon bonds, so straight away it doesn't even exist as an omega acid. This one here, we have 1, 7, so that's 8, 9. This is an omega-9 fatty acid, so not even omega-6. So it has to be D. But now let's just double check if it is D. I want to make sure we double check that. So, okay, so basically it's saying it has a molecular formula of this. Now, okay, so if it has a molecular formula of this, of course, you can write it like, I would basically like take, I would write it in this kind of form. So like take, write it like this, basically, COOH, like that. Okay, so basically, they should have this C15H29. Now, we already know this one had C15, which is good. We just need to check if the hydrogens are 29. There's 29 hydrogens. So this has 3 here. It says 8. That's 3 here. That's 3 here. That's 10. That's 2. So we have basically, that's basically 20. 3 plus 9. Yep, 29. Perfect. This one works. So it is. So this part here, we only need one. I'm not going to double check the other ones. But this one here has that molecular formula. So perfect. Done. That's nice. 21. Consider the reactions 1 and 2 at standard laboratory conditions. So we have reaction 1 that has this K value. Okay, and then we have reaction 2, which of the following is the equilibrium constant for reaction 2. One of the most easiest questions, gets, every time repeated in exam. So easy. So we could see that this whole thing has been actually flipped, like reversed. Meaning if it's reversed, you get 1 over K1. So if you're reversing this part here, you're reversing this whole reaction. You basically have to 1 over K it. Now we've got basically like this, close to this here. If you reverse it, and you can see everything's actually multiplied by 3. Like if you look at the water here, it was 1, but now they've multiplied by 3 also. So everything's multiplied by 3. So if you multiply everything by 3, you actually cube it. Power of 3, which is basically 1 to the power of 3 is just 1, which is just K1 to the power of 3. So it's actually C. Wow, this is nice. Question 22. The following reaction takes place under certain conditions to produce ethane amide, which is this. All right, 3 grams of acetic acid reacts to produce 2.4 grams of this. Okay, and we're given basically the molar masses of everything. The percentage yield for this reaction is what? Okay, beautiful. So we know yield is basically, we're trying to produce, of course, that ethane amide. So it's basically the grams. It's if you think about it, what's the formula? It's in your formula sheet. It's basically the mass, the experimental mass. So it's the experimental, I'm going to write EX, basically experimental mass of ethane amide. So because that's what we're producing, over your theoretical mass of ethane amide. That's basically, and we multiply by 100 to get it as a percentage. So let's do that. Well, we don't know the experimental, because they told us that when we reacted this, we already produced 2.4. So when they reacted it, we got an experimental value of 2.4 grams. How do we calculate the theoretical value? This is where we use stoichiometry. Oh my god, I can't even say it. Molar masses in stoichiometry. Stoichiometry. I can't even say it. Don't worry about it. All right, let's do that. So what I'm thinking is, what are we going to do? So we have 3 grams of acetic acid. So 3. Make sure we get it in moles. So remember, to get it in moles, it's mass over molar mass. So it's 3 divided by the molar mass, and we already know the molar mass of acetic acid is 60. So 3 divided by 60, we get 0.05 mole of acetic acid. And so basically, because all of them are 1-to-1 ratio from the equation, it means our mole of ethane amide is actually, so CH3CONH2 is actually the same, 0.05. Now we just need to get the mass. And remember, it's very easy to get the mass. It's the mole times the molar mass gives you the mass. So that's 0.05 multiplied by the molar mass of ethane amide, which we know is 59. We should get that. Times 59. We get 2.95. Done. Let's rub this rubbish out. It's too much rubbish right now. Too much of a mess. Okay. And multiply this by 100 to get the percentage yield. So 2.4, what about that, times 100. We get 81.4 basically. Easy. Question 23. A student performed a titration using a solution of 0.103 mole of ethanoic acid and a solution of 0.236 of sodium hydroxide. The allocate of the ethanoic acid was 225 milliliters, and the titer of the NaOH, so sodium hydroxide, was this. Which of the following explains the titer obtained by the student? So actually, let's calculate, because we can actually calculate it. So first, what we need to first do is write the equation, what's happening. What's the reaction of the equation? So basically, we're reacting ethanoic acid, which is CH3COOH, and we're reacting with sodium hydroxide. When you react with sodium hydroxide, we know that these are basically going to form water. This part here going to have to form water. And then we're going to basically be left out with NaCH3COO, basically. That's your reaction. Everything's everything is 1-to-1. So quite useless in a way, but yeah, nicely written equation. So now we can do some calculations. Now, we need to get because our sodium hydroxide is our standardized solutions in this case. We know its average titer is 11.6. So let's calculate the mole of it. So NaOH, which to do that, remember, so your formula, so concentration is N over V. So we know the volume multiplied by the concentration, so volume, so which is 11.6 times 10 to the negative 3, make sure it's in liters, times it by the concentration. Now, we know the concentration of sodium hydroxide is 0.236. That's going to give us 11.6 times 10 to the negative 3 times 0.236. We get basically 0.0027376 mole. Now, because it's a 1-to-1 ratio, we already got the mole of basic ethanoic acid, which is great. And so we've got that. And now, which is the same as this, basically. I'm just going to basically copy this whole thing here. Duplicates right there. Done. Now, we need to basically just get the... now we don't want to solve the concentration. To get the concentration, we've got the mole. We just need to divide by the volume of the allocate, which is 25 milliliters. So divide this by 25 times 10 to the negative 3, get it in liters. We basically now solve for the concentration. So doing that, we get 25 times 10 to the negative 3. Done. We got the concentration. So let's rub all this rubbish out and let's look at the question. So it's 0.109 mole. Look at that. So the actual real concentration is 0.103, but we've overestimated it. Look at our calculations. We got 0.109. So this could, this is an error, and that's what we have to look at. What could explain the titer obtained by the student? Titer. What could explain the titer obtained by the student? Student performed titration using that. The allocate was that. Was this? What could explain the titer obtained by the student? Easy. So like, they're basically explaining this. Like, why do we get an overestimation, I think. So which of these will give us an overestimation of our overall concentration? The burette was rinsed with NaOH solution. Rubbish, that's normal. That's what we do. We use the burette and we rinse it with our standardized solution, which in this case is sodium hydroxide. That wouldn't even affect it. That's the actual standard procedure that we do. So rubbish, that shouldn't even overestimate it in a way. The indicator used was a phenolphthaleate, I can't even say it, but alright. Now, to actually determine what indicator we should use, well, let's think about it. We have a weak acid. So weak acid, because we know that ethanoic acid is a weak acid. And we are reacting with a strong base, which is our sodium hydroxide. So sodium base. Now, think about it. Weak acid, you're reacting with weak acid with a strong base. Of course, you're going to get a stronger... overall, pH should be around closer to the base, because you should really have a strong base. So it should be around like... it should be basically like... because we know the pH of water is 7. It has to be greater than 7. Like 8 to like... basically like... we can say like 8 to 11, basically. A pH of 8 to 11 is the range of what indicator should be used, because remember we have a weak acid, which is like, of course, around 6 pH. No, 6 to 5 pH. And if you're reacting with a strong base, which is like 14 pH, you should get around 8 to 11 pH overall. So let's just check if phenylaniline is between something that looks like that, because if it is, makes sense, we should use that. Alright, let's have a look at this. Phenylaniline, which is here. So it is correct. So 8.3 to 10, which is like what we said. So around that range where you have, it's when you react a strong base with a weak acid, that's what we would normally use, phenylaniline. So that's wrong. Because it's correct. It is correct. Phenylaniline is correct, but it's wrong for like explaining why we have an overestimation of the actual answer. Next part. There were air bubbles in the burette. Let's think about it. Wait, if there are air bubbles in the burette, let's say you have this burette here, and you have air bubbles. Let's say, okay, this is the actual titer. And so if you have, let's say, say you actually have air bubbles, that would increase, like it would slightly increase the volume, because you know how there's air bubbles, it pushes up the water. Yeah, it would actually increase the volume that would be measured like this. It would actually increase it. Now let's think what would happen. So if we think about it, if you increase the volume using N equals, concentration times V equals N. So rearranging this. If we increase the volume, you basically increase the number of moles of sodium hydroxide. Because they are 1-to-1, it means you basically increase the mole of what we call your ethanoic acid. So the mole of ethanoic acid has increased. So using the formula again, N over V for the concentration, if your mole has increased, you have basically increased the concentration. That does actually explain it. It could explain it because we do have an increased concentration. So that could be possible. So I will put a tick on that. Not too sure about it, but let's look at the next one. The pipette was rinsed with water. So if your pipette was rinsed with water, your actual concentration that we got, which was 0.1039, would be underestimated. Why is it overestimated? It doesn't explain it. So rubbish. Because it would have been underestimated. It would have been like less than 0.103 if you rinse your pipette with water. So it has to be C. 24. Sulfur trioxide can be produced from oxygen and sulfur dioxide in the following equilibrium reaction. Consider the following statements about production of SO3 in a closed system. Okay, increasing the temperature of the system will increase both the reaction rate and the equilibrium constant. Let's break it apart. We're talking about first reaction rate. Remember, when we're talking about the reaction rate, think of collision theory. If you're increasing temperature, the molecules are basically having a higher average kinetic energy and they are basically colliding with each other, hence the frequency has increased. Yeah, they're colliding, and so your reaction rate would normally increase. So increasing temperature will actually increase the rate of reaction. Beautiful. But would it actually increase the equilibrium constant? Let's think about it. So because we know it's exothermic, energy would be released out. So imagine you increase temperature, so you increase energy. The system's like, oh my god, I have too much energy on the right side of my equation, on the products. I need to get rid of it. The way you would get rid of it is it will react on the backwards reaction to get rid of that energy and form the reactants. That will actually decrease the equilibrium constant, not increase it, because remember, your equilibrium constant is your concentration of products over your concentration of your reactants. If your reactants are increasing concentration and basically your products are decreasing, your K value basically decreases. So rubbish. Increasing the volume of the system will reduce the reaction rate and reduce the equilibrium yield. Let's have a look at this too. Just delete this. Let's have a look at that one. So if you increase the volume, you're decreasing the pressure. And remember, if you decrease pressure, it will decrease the reaction rate. Because, think about it, if you have a high volume, let's say you started with a low volume, basically. A small volume. And basically, you have two particles, they're colliding with each other because they're in a small vessel. But if you increase it with those two molecules, you've actually decreased the reaction rate because they have more space. They won't collide with each other as they were because there's more space for them to move. So absolutely yes, increasing the volume does actually reduce the reaction rate. And reduce the equilibrium yield? Let's have a look at if it would decrease the equilibrium yield. So, okay, we've increased the pressure. We've increased the volume, meaning decreasing the pressure. The system's like, wait, someone has decreased the pressure. I need to find a way to increase the pressure. Find a way to go back to my equilibrium to increase the pressure. The way you would increase the pressure is go backwards because it will form more moles. You got 3 moles in this side. So 2 plus 1 compared to this here. So that would actually what? Yes, that would actually decrease the equilibrium yield of SO3 because it's forming more of the reactants and hence decreasing the SO3. That looks good. So this one looks good. So, okay, let's look at the next part. Increasing the pressure of the system by adding nitrogen gas will increase the equilibrium yield of SO3. Rubbish. Nitrogen gas is not even in the equation, so take it out. I think a lot of students make that mistake thinking that, okay, you put nitrogen gas, so you should, do something with the pressure. But remember, if it's not in the equation, it does not affect it. It has no effect on the equilibrium yield of SO3. IV. Adding a suitable catalyst to the system will have no effect on the equilibrium constant. Absolutely, that is correct. We know catalysts don't even affect our equilibrium constant. It just basically increases the rate of a reaction. So that looks correct. So IV looks also correct. Which of the following statements above are correct? So it's basically 2 and 4. So C. Yep. 25. 1.3 grams of ethanol was burned in a fuel burner. The temperature of 500 grams of water in the beaker placed above the fuel burner increased by 20.3. The following events could have occurred. The ethanol was diluted so it contained 10% of water. Octane instead of ethanol was placed in the fuel burner, or heat was lost to the environment. Which of the possible events best explain the results? Okay, say 100% conditions, no heat loss. How do we find them? If you burn basically 1.3 grams of ethanol how much heat would be basically produced, so how much energy you would release. Easy, you use your actual data book, go down, where's ethanol's right over here, and what would be the energy multiplied by 29.6. You will basically release 1.3 times 29.6. You will release 38.48 kilojoules of energy. Easy. That is, if that's of course theoretical, no, 100% no heat loss. That's what it will look like. But because we've of course done like a experiment, we've used 500 waters in a beaker that was placed in the fuel burner, and we've increased. Okay, the temperature was increased, so we're going to use E equals MC delta T. But the mass of water is 500 times by 4.18, which is the specific heat capacity of water, and times it by the change in temperature, which is 20.3. We get 20.3. We get, make sure you divide it by 1,000 to get it in kilojoules. We basically get, so remember, this is your theoretical value energy. This is our experimental energy, so EE, which is 42.43 basically kilojoules. What the hell? How do we get our how do we overestimate our energy? Damn, we've overestimated the energy, which is something that's crazy. How? Well, let's look at the events now. The ethanol was diluted so that it contained 10% of water. Rubbish. If you actually had water in the ethanol, most of the energy would have been given to the water to evaporate it. And so your energy, your experimental, this energy here, would have actually decreased less than that 38.48. But we can see that it's overestimated, so that's rubbish. 2, octane instead of ethanol was placed in the fuel burner. Could be. Let's check if octane actually has a higher energy value. Because if it does, yeah, he could have messed up by putting octane, not ethanol. Well, octane, yeah. You can see that octane actually has a 47.9. It's actually higher. So if you did use octane, it's basically, so 1.3 was it? 1.3 times 47.9. You basically would have released 62.27 kilojoules. Yeah, very, very high. Absolutely. So, yeah, they could have messed up by putting octane. That looks suitable. Heat was lost to the environment. What? If you lose heat to the environment, your experimental value should have decreased, which is rubbish because we've overestimated it. So, not 3. Which of the following possible events best explains the result? So, only the second one, I. What? All the answers... Only this one has I, the second one. Whereas the other ones all have, like, why would they consider also 3 is correct then? Heat was lost to the environment then. Why would they do that? If octane instead of ethanol was placed in the fuel burner, why? Heat was lost to the environment. I know the second one is correct, but... And it's because it's the only one that's actually... Did they make a mistake? Heat was lost to the environment? Or if they're doing this, this is really not... I think it's stupid if they're doing this. Did they basically take this over here? So when we're saying with the second one, octane instead of ethanol was placed in the fuel burner. So your actual energy that was going to be normally... Your theoretical value that was released would be this. But because our experimental value is less, meaning that... So this was ethanol and it's basically... We've had heat loss, and hence we've got this value here. But why would they do that? That doesn't make sense, especially if students... Yeah, it could be that. But I know it's actually 100% the second one, so I'll say D. If they're doing that, that's stupid. So what probably they're doing right now... so this is your experimental value, if they used octane, and basically they've decreased the... because they've had heat loss, so down with the third one's probably correct. They've got the experimental value of this, which would make sense, but... That's too much work for a question like that. So I put D. Question 26. The organic compound Z react with hydrogen iodine in an addition reaction. Easy. So if hydrogen iodine actually reacted in an addition reaction, it has to have a double bond, like a C to C double bond. That is a hint they've given us about this compound Z. And the infrared spectrum of the compound Z is shown. Yep. The compound Z could be what? So first, what I'm going to do is draw all of them. See which ones have double bonds, a C to C double bond, and those are likely to be our correct answer. So let's draw each one of them. The first one is C. It has to have a double bond. C, COOH. Good, yes. You know, hydrogen and iodine can actually react. So here and here, and break that bond. So this one, possibly correct. So we can put a tick on that. Next one is, all right, so no, this one is rubbish. There's no actual double bond. You can see that. If you graph it, it looks like this. It has not even double bonds. I C to C double bonds. So rubbish. Next one, let's have a try at the next one. So we have a C here, and a COONH. Rubbish, no double C to C double bond. So also that one doesn't work. D, so we have nitrogen here, C to C double bond. Good. And a C. Okay, this one actually, yep, possibly could work. We have a C to C double bond. So when you react with hydrogen iodine, it will be basically like it will break this double bond, and it will have hydrogen iodine in it. So A and D look correct, basically. These could be possible answers. And to kind of distinguish, we're going to use our actual IR spectrum right now. So basically, by looking at the IR spectrum, we have this very broad, strong peak, which normally indicates that it's an OH group. And we can also see this strong peak at this around 1,700 frequency. Likely, it's actually a C double O. So C double O normally. That's from my memory. So I've done these questions for a couple of times. So I've kind of seen the kind of figures quite a lot. So yeah, it looks like this. Now, if you were in this exam and say, of course, you haven't memorized, it's okay because you have them in your data book. In my data book, I've actually placed this, this nice figure, which is not in your data book, but have a look at it. So basically, this is what it is. Basically, you can see that if you have a peak from 400, so here, from 2,500 to 400, so which is here, in our case, here to here, it would likely indicate it's a NH group, NH, OH, or CH. So any of these groups. Now, of course, it's not a CH, so it could be just it's normally known as OH or NH. It's like a nice kind of figure you should memorize in your brain. It is so helpful when you're doing these questions. Now, we also have we have also a peak from our one from 2,000 to 1,500, which looks like, as you can see from this figure, it could be these. So a C double O, or it could be a C double N, which was not part of any of those equations, or a double bond. Now, basically, those equations did have a C double C, which I don't think it's very useful to even write that, so yeah. And that's it. Well, and this here is your fingerprint region, so you don't want to touch that. This is one of the best and quickest ways to break a question down. Now, both of them all have the C double O, so that's not very useful. Now, if it's an NH, it would be D, but if it's an OH, it is an A. So how do we determine what it is? Easy. Go to the next section. The next section is going to basically help you out. So the next section, if you look at it here, is it an OH? Yes, it is an OH. Look at this OH here. The OH here has to be a strong and broad. What do we mean by broad? You can see it's a kind of a broad, but it's strong. And you can also see it's actually strong. If it was an NH, for example, where's an NH? Where's the NH? Amine group, like this example, it's medium. Medium means like, it's normally not strong. It would be like this. It would be strong. It would be like very strong, but it won't be broad. It's normally like narrow, basically. A little bit narrower than compared to an OH group. So yeah, that's what my thingy is. So NH. Yep, that's it. So it's normally like a medium. It's not that basically strong too. So it's an OH, likely to be an OH, not an NH. So it has to be A, because D has an NH too, so it's rubbish. I hope that kind of makes sense. Using this here is one of the most helpful data books. I've also put this in my data book just so some of my students can really understand. These are one of the most easiest questions to get full marks on, because if you have this here, it really helps you out. All right, that is done. Yep, so 26 looks good. Next one. 27. So this is for 27 and 28. The proteins in a sample of cow's milk are analyzed using high-performance liquid, so HPLC, using a non-polar stationary phase and a polar mobile phase. The results are shown in the chromatograph below. Okay, Question 2017. Which of the following options correctly describes how a change to the experimental conditions affect the retention time of T and the separation of R and S? So let's think. Let's look at the first one. Changes to the experimental conditions. Let's look at the first one. Decreasing the column length. What happens? So what happens to the retention time of T? Where is T? T is here. So we can see that T is actually on the right, where it actually has a high retention time, meaning it's basically, because your stationary phase is very nonpolar, it means that T is likely to be very strongly nonpolar, because it has a very long retention time, so it's kind of very, it's very bonded to that nonpolar stationary phase. That's why it takes a very long time to get out. And so what's happened here? What happens to the retention time of T if we decrease the column first? Let's look at this part here. Decrease the column. Say you had a high column, like a very let me just draw it nicely. Oh man, it's not the most, there it is. Okay. So we have this nice, basically it does the job basically. So let's say we had a column like this. You can see it's very large. And so let's say we started with this. Now, remember it's compound, so what am I saying? It's a non-stationary phase. The stationary phase is non-polar. So imagine T. T basically is very, because it's very, it likes to bond with because it's also non-polar, it likes to basically bond with that stationary phase. So it actually takes a very, very, imagine it's taking very long for it to kind of, because it's bonding with that stationary phase, it's taking very, very long to actually go down and be released, coming out of the thing, and hence, therefore, when it comes out, that's when the retention time is basically measured. So yeah, because it's very bonded to that stationary phase. It takes very, very long time to come out, so its retention time is higher. But what about if we decrease now? Because we said we wanted to decrease the column length. What happens if you decrease the column length? Let's have a look at this. What happens now? So, again, because it's of course, it's very bonded to that stationary phase, it's going to be very bonded, but when because it's, it will actually, its retention time will decrease, because imagine it's very bonded, but because of the length is very less, it doesn't have a lot of time. It doesn't, have a lot of time where it's basically bonded, and then when it finishes bonds, it leaves. Compared to this, where the column's length, and it has a very, very long time for it to be bonded, so it takes its time and then release. Whereas here, you can see that, yes, it's taking its time, but because the length is very short, it gets, after some time, it gets released. And then when it's released, it means its retention time is less. Makes kind of sense. So let's say it took 20 minutes to come out here. It would take 10 minutes to come out in here. So we can see that the retention time of T would have been basically decreasing. So not B, so it has to be decreasing. Wait, what about C? Increasing the column temperature. Let's have a look at these here. These ones here. What happens if you increase column temperature? Well, let's break it apart. So you have one here. Okay. So you have that column there. And so basically you have, T, the molecule T. And, because it's very bonded to that, it's very bonded to the stationary phase, it takes a very long time before it gets, comes out of the tube, and hence gets, the retention time is measured. So, yeah. Now, think of that like viscosity. Think of it as honey. The molecule is actually like honey. And when you put it in a tube, it takes very, very long time until it just releases. Think of it like that. So basically, currently, it has a high viscosity. And if you increase the temperature, what happens? When you're increasing the temperature, you're bringing those intermolecular forces with the stationary phase and the molecule itself, meaning that it doesn't actually bond to it. It will actually then release quickly because it's not bonded to it. Just basically, because it's not released, it will basically not bond to it, but it will less its intermolecular forces are basically a little bit destroyed. Hence, your viscosity is a little bit decreased. Think of it now like water. Straight away, just goes out. So what's happened to its retention time? Because it comes out quicker, the retention time has decreased. Again, it took, let's say initially it took 20 minutes because you've basically increased the temperature, broken those intermolecular forces, hence your viscosity has decreased, you'll fall quicker, and hence your retention time. Let's say it takes 5 seconds to come out of the tube. So the retention time actually decreases when you increase the temperature. So not D. So we only have A and C. Now, let's come back to A, where we were talking about decreasing column length. in terms of separation of peaks of R and S. What does that do? All right. So what is R and S? R and S are like molecules. You can see that they're closely related molecules because you can see that they're like very like put to each other. Now, of course, they are different molecules, but they are very kind of, in terms of, they're very common to each other. You can see that they are kind of separating. You can see that they are basically kind of separating here. Yeah, totally different molecules, but absolutely, you can see that they have so much things in common. Now let's have a look at what happens when you decrease the column length. So the thing is, if you actually have a high column length, if you have a very high column length, like a large column length, this is good because say you have those two molecules. Say this is R and S. You can see, of course, S is more bonded. You can see that S is more bonded to the stationary phase because it has a higher retention time. So imagine this here is S and this here is your R. You can see that S will be slower. Like if you give a very large column length, it's good because you can see that it gives them more time to separate. You can see that R would take it, where S will, of course, it's a little bit slower, but R is a little bit quicker because it's like less, non-polar. So yeah, if it's good to have a very high common length, like a very long length of a tube, because what will happen is they will separate. They'll actually have more time to separate. Whereas this one here will separate. Whereas this one here will separate less, but they will separate in some time being. The longer the length, the more separation they have, and hence when you actually look at it here, it will look like this will be R, and let's say this will be S. You see that they are basically now separated. So yeah, basically, whereas if you look at it from the small column, they don't have a lot of time to be separated. Imagine this is your S, and this is your R. Yes, R is basically R is going down quicker, whereas S, yeah, it's also going down, but they don't have a lot of time where they're actually separated. Like they would basically go down, yeah, and because the length is less, there's no, there isn't a lot of time where they'll be much more separated. Hence, yeah, it will likely actually decrease them. There'll be basically more. So the separation between R and S, when you decrease the common length, it's even worse because they don't actually have a lot of time to be separating from each other. So if you think about it, separation of peaks in R and S, if you decrease the column, it will actually decrease. This one looks good. Yeah, so because there isn't actually, they don't have a lot of time to separate from each other if you decrease the column length. So yeah, I hope that makes sense. It is a lot. I think I'm talking a lot, and it's a little bit kind of hard to explain these stuff, but yeah, that makes sense. What are the S? So come back to that increasing column temperature. So it says separation of peaks on RS should increase. Let's think about it. All right, say we have R and S here. S and R. Yeah, very closely related molecules, we can say. Very, very closely. So let me put that there. Okay. Like we said, if you increase the temperature, you're breaking those intermolecular forces, and hence they are coming out quicker. They're coming out quicker. So if you have these here, they're basically coming out quicker. Now, if you think about it, if they're coming out basically like quicker, so sorry, what am I saying? So increasing the column length temperature, so what is separation of peaks in RS increases. So the separation of peaks in RS increases. So wait. So when let's think about it in terms of viscosity. So imagine they have a high viscosity. If you increase the temperature, the viscosity basically decreases, and hence they will come out quicker. And if they come out, think about it, if they come out quicker, they don't have a lot of time to separate from each other. So if they don't have a lot of time to separate from each other, so think about it like this. They're basically like, imagine they're separating, they're taking their time to separate each other, but if you increase the temperature, they're coming out of the tube quicker because they're not actually bonding to that non-stationary phase. So, and hence they won't even have a lot of time to basically separate from each other, meaning that the distance between R and S should be decreasing because they're not going to be separated from each other. They don't have a lot of time. But yeah, so C is wrong because it's saying it increases, the separation increases. It actually decreases. So it has to be A. Wow, a little bit harder question to kind of think about, but I hope that makes sense. 28. A manufacturer claims that there is 2.6 grams of protein Q in 240 milliliters of cow's milk. Standard solutions of protein Q ranging from 0 milligrams to 50 milligrams per liter are analyzed using HPLC. A calibration curve is constructed from the results. The calibration curve is used to accurately determine the concentration of compound Q in the cow's milk. What size of volumetric flask should be used to dilate that 1 milliliter of alicate of cow's milk? I think I've seen this question from one of the past papers. I think it was like 2018. Don't remember what paper, but it's one of the most easiest questions. It's like, they basically just repeated the question. So what you should do is, okay, we want to get it in terms of this. So you know that 2.6 grams of basically protein Q in that 240 milliliters. We want to get it in this unit, milligrams per liter. So think about it. It's in terms of grams. We want to get it in milligrams. So we actually should times it by 1,000. So that 2.6 times it by 1,000. You basically get 2,600 milligrams now. That is just converted to milligrams. And you can see now we get, but basically they're divided by per liter. This is a milliliter. So make sure you divide it by 240 times 10 to the negative 3 to get it in terms of liter. So 26 divided by 240 times 10 to the negative 3. Now you get 10833.3 milligrams per liter. Good job. That is perfect. So we've got our actual value here. Now, what size of volumetric flask should be used to dilate? So we need to find the dilution factor. So think about it. This 1 milliliter, you're going from 1 milliliter. Let's try the first one, 50. You're going from 1 to 50 milliliters. So the dilution factor is 50. Divide this by 50. And if it's in this range here, from 0 to 50, it's the actual best one to use. So if you do that, divide that by 50, you get 216.6 milligrams per liter, which is a problem for us. That is not in this range. So that's wrong. This is A. What about if you do 1 to 100 in the next case? So basically divide this by 100. What happens now? Does it fit in that range? 3 divided by... You get 108, which is still does not fit in that range, so wrong. What about the next one? 200? What about if we put 200? 1 to 200 ratio. Let's try that. You get 54. Now that's close, but it's again still out of that range. So it has to be D. Now let's just double check D. If we do 1 to 500, so dilution factor is basically 500. You get, yes, 21.6 milligrams per liter, which is in this range. That's actually going to be very useful. So D would be the answer. It's one of the kind of easy questions to kind of fully get. It's, because it's kind of repeated in so many past papers I've done. Yeah, very, very nice. Yep, what size of volumetric should be done? Beautiful. Next question, 29. Consider the following equilibrium reaction. All right. So in system X, 2 moles of CH4 and 1 mole of H2 were added to an evacuated 1 liter container at 25 degrees Celsius. In system Y, 1 mole and 1 mole of H2 were added to the different evacuated 1 liter container at 250, so 25 degrees Celsius. Which of the following statements is correct? The initial rate of the forward reaction would be higher in Y than X. Let's think about it. So in system X, let's look at system X. Because you got like 2 moles of CH4 and 1 mole of... Okay, look at Y first. You're basically putting 1 mole of CH4 and 1 mole of H2O. And basically that's, of course, going to go to the forward reaction. It's going to form these two here. And so, it will form these. But if you have 1 mole of this and 2 moles of CH4 in comparison to the other one, remember, you have more molecules. You actually have more, molecules that are able to basically hit each other. So the more molecules, so the frequency of collisions basically is greater, meaning that your rate of reaction is going to be faster going forward in comparison to basically Y, because you have more molecules that are going to be colliding. So your rate of reaction for X should be higher than Y. Whichever the initial rate of reaction for the forward reaction would be higher in Y than rubbish. X will be higher than Y. B, the concentration of H2O would be lower in system X than system Y at equilibrium. Let's look at that. So the concentration would be lower. Okay, so let's think about it. Let's say at Y, let's look at Y in this case. You have 1 mole of this and 1 mole of this, you react it and you form this. All right. And of course, when you're forming these, these will decrease. These two will decrease. All right. Makes sense. So X, okay. But what about if you had 2 moles of, CH4 here for the, system X? This is a bigger problem because you're going to be forming more. It's going to be a stronger rate of reaction. You're going to basically you're going to be forming more of these, and hence these here will basically decrease like more down. These two will be decreasing more down. Hence H2O2 will actually be decreasing more in X. In system X, it will actually be decreasing more. H2O2 would be lower in X than system. Yep, that looks actually correct. Yeah, the concentration of H2O2 would be lower in system X than in system Y. Yeah, that looks good. So it would be in, because it's going to basically go more in the forward reaction and hence use all of the stuff here in comparison to using 1 to 1 mole because you have more of the CH4. Let's have a try C. The rate of the backwards reaction would be the same for the 2 systems at equilibrium. The rate of the backwards reaction would be the same for the 2 systems at equilibrium. Let's have a look at that. So if you had, let's say, Y, we had 1, okay, so basically, while you're forming, when the reaction is going to the right, you're forming these here. But when you're forming this, because it's a reversible reaction, when you're forming this, you're going to have also a backwards reaction. Okay, you get backwards reaction, makes sense. But, okay, yeah. But if you have, let's say, 2 to 1 here, you know how you form this quicker? Because you form these basically quicker. When you're forming these quicker, you're basically going to be forming the backwards reaction much quicker. So basically, the rate of the backwards reaction, the initial would be quicker. They won't be equal. In other words, the rate of backwards reaction won't be equal because in terms of X, it will actually be higher. The rate of reaction will be actually higher than Y. So they're not going to be equal at equilibrium. D, the concentration of hydrogen gas in X would be the triple the concentration of H2O2 in gas in system X at equilibrium. Let's think about that one too. So the concentration of hydrogen gas in system X would be triple the concentration of H2O2 in system X. Let's think about it. All right, so we're looking at X. This is a 2 to 1 ratio. So basically, because we have so much amount here, no. They're being idiots. If it was a system Y, it would kind of make sense. If it's So when you basically mix these, it's gonna form 3 moles of hydrogen, hydrogen gas, and 1 mole of, and you'll lose 1 concentration of H2O2, which would make sense in Y. But think about the other one where this is 2. You have 2 of these. Because you have 2 of these, you're gonna basically not form 3 times the hydrogen gas. You're going to be basically forming more of it, not just the 3 mole of hydrogen gas. Hydrogen gas. You're going to basically form more because you have more of the CH4. You have 2 moles of it, not 1. So the ratio, it's not a ratio because you have 2 moles. So you actually form more of this 3 times the hydrogen gas in our X. The concentration of H2 in system X would triple the concentration of H2O2. It will not triple. It will be more than triple actually. So that's not right. So B would be the best in this case. Question 30, last question. Which molecule can exist as a cis and trans isomer? Easy. Let's have a look at the first one. Pent-1-ene. Let's draw that. Pent 1, 2, 3. So it will look like basically like this. So C double C. You have a hydrogen here. You have a C here too. So you have a CH2, CH3, and HHH. Now, for it to be an isomer, like a cis and trans isomer, first law, make sure in every carbon here, in that double bond, they need to have different side groups. Nope, wrong. These have the same. They have hydrogen, wrong. Whereas these ones, okay, they fit the description, but these two have, 2 hydrogens on both sides, doesn't work. Let's try the next one. So 1, 2, 2. That's what it looks like. And it is, so if I was graphing this, it'll be here. And it'll be CH2, CH3, H here, CH2, sorry, CH3, and a H. What about this one here? all right, totally different side groups. You can see in this carbon, you got different side groups, and also in this carbon, you also have different side group. Works perfectly. Now let's check if it works in a cis and trans. Yes, it does work in a cis. Look at the both hydrogens on top. And if it was to get it trans, what about if you rotated these two? What about if there was a rotation between these two? Then it would fit also a trans. Look at that. It also fits a trans isomer. So this B looks great. This looks good. So let me just rub these out and let's do the next ones. 2-methyl butane. Okay, so but1 double bond butane. So if I draw butane, so 1, 2, and it has a methyl here. So if I was graphing this, it would look like hydrogen, hydrogen, CH3, CH2, CH3. Now look, these do have, on this carbon, do have different groups, but this one have the same groups. Hydrogen, hydrogen on the same carbon, wrong. Does not meet the, it cannot be an isomer of a cis and trans. Last one, butane. So 1, 2, 3, yeah, that's that. 1, 2, methyl. Looks like that. So it'll look like CH3, H, CH3, CH3. Now look, different side groups on this carbon, but the same side groups on this carbon won't work. So only possible answer would be B. Not an actual bad, multiple choice questions, I think. A little bit, this one's 29, I think a little bit would twist people's heads. But overall, I found it not too bad. I hope you guys enjoyed this video. Please, I hope you learned something from this video. Please make sure to like and subscribe for more future videos like this. And yeah, I hope it kind of helps you in any way. And yeah, I hope you guys have a great day. Take care of yourselves. Bye-bye.